This is the lecture for 4.4. This is logarithmic functions. Let's see. All right, so in the last section, in 4.3, we looked at exponential functions. And here's a very rough graph of kind of the basic exponential function. This was f of x equals c times a to the x. So a couple of questions we could ask about this function. First, is it a function? Well, yes, because of the vertical line test. And then the second question we could ask is this function one-to-one? And if you remember from section 4.2, I think it was, in order to determine if something is one-to-one, you can do the horizontal line test. And if that horizontal line crosses at most one time, then the function is one-to-one. So this function is one-to-one, which tells you that it does have an inverse. Okay, so that inverse is what we're going to look at in this section. Let me draw the graph again. Okay, so it passes through 0, 1. Here's that exponential function. To find its inverse, we're going to reflect it over the line y equals x, which is this dashed line, kind of diagonal, 45 degrees through the origin. So when I reflect the graph of y equals c times a to the x, this one, over the line y equals x, get the graph that looks like this. And this is the function log base a of x. Log base a of x. So this is the inverse for the exponential function. All right, so let's look at a couple of forms first. Okay, so exponential form is when you have a base raised to a power, and that gives you an answer. That's exponential form. Fairly familiar to us. Okay, to write the same thing in logarithmic form, this would be log with a base of 3, so this base of 81 equals 4. So what you have is the log base 3 of the answer equals the exponent. So this is logarithmic form. Or you could say log of a base of the answer equals the exponent. So you can change back and forth between exponential and logarithmic form depending on what you're trying to do, what kind of thing you're trying to solve. And so for the next question, we're just going to change these to logarithmic expressions. Okay, so here's the first one. 1.2 raised to the third power equals m. So this is currently in exponential form. To rewrite this in logarithmic form, it will be log base 1.2 of m, the answer, equals the exponent 3. Okay, let's do another one. E to the b equals 9. So this will be log base e of 9 equals b. And log base e later we'll talk about is ln, but I'll just write it here for you now. Okay, sorry for the delay. Next part, same thing, one more of the same thing. A to the 4th equals 24. Okay, so take a second and rewrite this in logarithmic form. So this will be log base A of 24 equals 4. And so here's the basic form: log base answer exponent. All right, let's go the other way now and change these to exponential form. Okay, so we'll start in logarithmic form. Log base A of 4 equals 5. Okay, so the base is the small number. The exponent, or the power, is what's on the right side by itself, so A to the 5th equals the answer 4. Okay, same thing, try this one. Log base 3 of 5 equals C. So I can rewrite this as 3 to the C equals 5 in exponential form. Okay, so often it's useful to think in terms of exponential form in order to solve something, just because that's what we're more familiar with. Okay, so the next question will say evaluate. It means you're going to give a numerical answer. So log base 2 of 16. I'm going to think about this in exponential form. Right now it's not an equation. Let me just add equals x. Even though that's not part of the original, it helps me think about it. Okay, so rewrite in exponential form first. 2 to the x equals 16, and then we'll just think about it. 2 to what power gives me 16 as an answer? So 2 times 2 is 4, times 2 is 8, times another 2 is 16. So 2 to the 4th power gives me 16, which means my x, the exponent, is 4. Okay, let's try another one. Log base 3 of 1/27. Okay, again, it doesn't say equals x in the problem, but I'm going to add that to make it easier to think about. So base to the power gives me the answer. So 3 to the x equals 1/27. Okay, so 3 to what power gives me 1/27? Well, let's just think about the 27 first. 3 to what power gives me 27? So 3 times 3 is 9, times 3 is 27. So that's the 3rd power. But to get it to flip to the bottom of the fraction, that exponent will need to be negative. So this will be x equals -3. So 3 to the -3rd power is 1/27. So the answers we were solving for here in the original log form are actually the exponents when we write these in exponential form. All right, let's go ahead and look at the graphs. Okay, so we're just going to graph log base 10 of x. You can do any base. 10 is the common base. Okay, so we'll do this again using a table. Here I want to plug in things that I know are powers of 10. So I'm going to plug in 1, 10, and 100. There are lots of other choices, but that's a good start. So if I plug in 1 right here, that's saying log base 10 of 1. So in other words, 10 to what power gives me 1 as an answer? How do you get 1 as an answer? That would be 10 to the 0 power. Okay, plug in 10, so log base 10 of 10. So that's saying 10 to what power gives me 10 as an answer? That would be 1. 10 to the first power gives me 10. And then finally, plugging in 100. This is saying 10 to what power gives me 100 as an answer, which would be 2. Okay, so I'm still kind of thinking in exponential form over here. All right, let's graph this. Let's see, I need lots of x values. Let me just do up to 100. I'll count by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then for y's, I'll just count by 1. So definitely not a great scale, but at least it lets me show you. Okay, so first point is 1, 0, which is very close right here. And then 10, 1. And then 100, 2. Okay, so this is the graph of log base 10 of x. Okay, some properties of this graph: the domain. What x values can I have? It does get very close to the y-axis here, but does not cross it, so that domain is just from 0 to infinity, everything to the right of my y-axis. Okay, the range here, it does increase very slowly, but continues to increase, so this is going to be from negative infinity to positive infinity. The x-intercept I have as part of my table. It's the 0.10, this first one. The y-intercept here, this does not ever cross the y-axis, so there is no y-intercept. The vertical asymptote is x equals 0, so it's getting closer and closer to the y-axis, but not touching it. It is also smooth and continuous, just like exponentials. And it is increasing, at least this particular one, all the way from left to right. Okay, so this is the basic graph, or you can also refer to the first screen where I showed you the reflection across y equals x from the exponential graph. All right, so a couple of specific logs. We just did log base 10. This is called the common log. Ooh, the writing's terrible. Let me just go to the next screen. Works better at the top of the screen. Y equals log base 10 of x. This is called the common log. On a calculator, they will actually leave out base 10. So you'll just see log of x. It's like an understood base 10 that's not written here. Another kind of popular one is log base e of x, and that's that 2.718, that number. This is called the natural log, occurring in nature. And it is also written as y equals ln x. So instead of log base e, they'll write it as ln. Okay, so these are both buttons on your calculator, log and ln. All right, I'm going to go ahead and stop this presentation and start another one for solving logarithmic equations. That will be a continuation of 4.4.